We've been communicating for quite some time on LinkedIn and Slack about formal methods and exchanging papers and stuff. And so it's really fun for me to be able to have you come give a talk today. And I know more people will watch it once we post it online, if that's okay with you.
Yeah,
Um,
sure. Please, go ahead.
okay, cool. So I'm recording, but I'm going to crop the recording to begin with my introduction now, and not include our chit chat at the beginning.
Got it. Makes
Um,
sense.
Cool. Well, with that, I'll just give you the stage. I'm really excited to hear about your research, and yeah, really appreciate having you in the group.
Okay, so I'll go to full slideshow mode. Let me know if you can still see the screen properly.
Okay.
This is
Yeah, it's
visible.
it's perfect.
It's perfect. Cool.
Yeah.
Yeah. So firstly, I should thank Max. Oh, wait, what is happening? Firstly, I should thank Max for this opportunity. It's been a long time due, and yeah. So let's get to it. It's a very complicated way to try to give a talk on this topic, okay? Because there are just too many factors that are going in. I'll try to do as much justice as I can, and of course, I cannot do proper justice. Let's just keep it at that.
By the way,
Okay,
Ramit,
so
just so you know, in terms of audience,
yes.
Daniel's a PhD student in formal methods. Prashant has a PhD in kind of FM and security related stuff, LangSec.
Hmm.
Chris has a master's in mathematics. So I
Okay.
think broadly speaking, you can assume pretty high mathematical literacy, if
Okay.
if
Cool.
it's helpful to do so. Yeah.
That is helpful one. But the other thing is, but even then, my talk is dumbed down. I mean, I'm hoping it is. I'm not sure. It should be dumbed down to someone who doesn't even know this kind of things. Okay. So I'm hoping it is. You can like complain afterwards if it is.
Sounds good.
Okay, good. Okay, let's get started. Thanks, Boston Computing Club, for this thing. So this is descriptive complexity and introduction. So the first question, the question that we are trying to target is what is computation? At an everyday level, we use our smartphones, laptops, calculators to offload certain critical and tedious tasks. To notify us of our location, these devices are able to compute our global coordinates. To connect us with a friend, the push button systems make it immediate, even when they are continents away. To hitch a ride or order groceries, we find these devices sufficient. These devices are nothing but limited physical realizations of the Turing machine. So here I only mention the things that we interact with at an everyday use, but computation can be more general. We can talk about nature somehow being able to compute stuff and all that things. But I don't want to get into that. Let's just get deeper into closer to towards our goals. The theoretical computer science community is engrossed over this fascinating realm that arises out of the simple taken for granted question above: what is computation? This talk is geared towards introducing one such area called where computational complexity, classes, and logic interact. But wait, what are they, right? Yeah. So the topics that we will cover today, we'll just give everything will be very brief, short snippets and introductions. So Turing machines and computational problems. Then we'll get into complexity classes. We'll look into the p time polynomial time and p non-deterministic polynomial time. Then we'll look into mathematical logic and a very quick segue, which I'm pretty sure it doesn't do justice to the entire thing. But what do I mean by a logic L? Capturing a complexity class C and the theorems from the research, so that so that you guys can like go ahead and do your own research further. So this will be just an introduction to this entire thing. I won't go into the theorems, but I'll just give you a flavor of what kind of theorems are proven in this area. So introducing the Turing machine. So Alan Turing, 1936, PhD student of mathematical logic, came up with the following abstraction for a model of computation. So Turing machine is a septuple. You have Q, a set of states. Say sigma is a set of finite input alphabet. Gamma, a finite set of tape alphabets, which is a subset of the input alphabet, which is a superset of the input alphabet. Delta, which is the transition function, its inputs are Q and the tape alphabet, like the state that the Turing machine is in, and the tape alphabet that you are currently on, into a subset of into the power set of Q cross gamma cross left or right. So L and R is supposedly to mean that Q0 is the start state, and you have a subset from the set of states as QA, which is the accepting states, and QR, which are the rejecting states. A picture is of this particular form. You have this tape, input output tape like RAM, and then you have a control, and you go ahead, read the point on the tape, and based on which on the transition function, you should be able to like go to a different state and do some changes to the Turing machine and all that. So the first thing is like this is close to the so from this abstraction of the Turing machine, von Neumann gave you the separation of the data and the control, the ALU and the RAM and all, and that is where we have our current realizations of a computer that we use. Okay, but the thing to note is computers are limited in the sense that the tape is not infinite. So ultimately, you can whatever computer you have, with whatever configurations it is powerful enough, it can be actually combinatorily exploded into a large DFA, whatever that is. It's a finite automaton, which is a subset, which is something smaller compared to what a Turing machine can be able to do. So Turing machine is much likely much larger. So definitions, a deterministic Turing machine. So the way I had defined the transition function, it was like from a particular set of it was going to a set of states. So if these number of set of states are always one for all q and all tape alphabet, then you call it deterministic. So it's an edge out of the set of state, the state and the alphabet that you are at. So configuration, it is the information of the tape content, the current state, and the position of the head. That is the configuration. So configuration is a subset of gamma star. So this is the tape content. Cross Q, which is the state that you are at, into gamma star, wherever it goes with what changes it does. Okay. So a run of a Turing machine is given a Turing machine S, uh, where you have strings from the input alphabet. The sequence of configuration of the Turing machine M is called a run. And halting input is when a Turing machine operating on this input string S ends up in a configuration state, which is either the accept or the reject state. Then the Turing machine is set to halt. And it is not a given that for all a priori that for all strings a Turing machine will halt or not. So if a Turing machine halts on all their strings, it is so understood that it is a decidable Turing machine and it is an algorithm. So I've not written it down, but this is something that I should have mentioned. So language, the set of all strings accepted by the Turing machine, which is a subset of sigma star, which is your input alphabet. That is the language of a Turing machine M. And this language is decidable if there is a halting Turing machine M, such that L is equal to or the whatever the language of the Turing machine is. Okay. So what are computational problems? Sorry, I'm going a little fast. I have to cover a bit of things. Please keep a track of the time, and you can of course ask me questions. So first, to sort of explain computational problems, I think someone has a question in the chat. In case someone doesn't, oh,
Yeah,
yeah. So
yeah.
Max is and with his helpful pointers. Yeah. So my physicist friends have to deal with huge matrices of the size, say 1,000 cross 1,000, to figure out certain properties of interest, whether, say, the upper LU decomposition of the matrix is of some pattern or something of that sort. So, of course, this is in our common vocabulary, like how we discuss things, is a computational problem. But since computers do solve such problems, and since computers do solve such problems, of course, a Turing machine will also be able to solve this problem. But in the TCS community parlance, this would be termed as an instance of a problem. The problems we seek would be of the nature for any n cross n matrices. We would like to know if there is a general uniform recipe or a technique to discover the properties of interest. So we do not define our computational problems with a fixed value of the size of the problem. We talk about in terms of them being general for any arbitrary n. The problem statement is of this particular nature, and can we do something about it? So in this setting, whatever algorithm we come up with will have a generalizing flavor to it. And this is how we sort of bifurcate from what we understand in the theory landscape and what we understand in practice. So it might so happen, practice-wise, that the physicist comes up with a clever algorithm of finding properties of interest for the particular 1,000 cos 1,000 matrix to run in, say, 1,000 square plus 5 into 1,000 square steps. But the general algorithm that can try to solve the n cross n many matrices has a running time of n cube. So that, which means that 1000 cubes. So definitely not always the best that you can think of. But the idea of it is we want to talk about we want to get closer to a computational realm where which is abstracted away from the details of the machines that you are talking about. Say it should not depend on the Mac machine or the Intel machine. So you have this real RAM model. I have not written down that as well, which sort of calculates these steps and talks about some things closer to a platonic reality of things of a Turing machine working on a algorithm. Okay. Huh. So an example of a computational problem, primality, it is the natural number n a prime. The problem of primality belongs to the space or domain of natural numbers. A set of primes are 2, 3, 5, 7, 11, and the list goes on. And you can represent them as n belongs to n, where n is a prime. So n is a prime is something that we understand, but can we have an algorithm which the computer can also use to figure out? So to represent it as a computer program, we need to encode it properly. Usually the choice of encoding is a binary. So prime can be represented as so 10 is 2, 11 is 3, 101 is 5, and so on. So given the setting of computational classes, let's try to understand what complexity classes are. uh, on a high level, complexity classes are a set of problems. So now you had a computational problem like primality, but then you will have a bunch of such problems that take a similar range of resources to solve. So what do I mean by resource? Resource examples would be, say, all problems solvable in polynomial time with respect to input size, and all problems solvable in exponential space with respect to input size. So in this particular setting, the resource uh, would be time for the first example and space for the second example. So space is usually to do with the Turing machine take, and time is the steps that the Turing machine takes to sort of unroll and figure out the answer, get to an accepting state for the algorithm. So again, definitions. So let L subset of sigma stars, sigma being 0 and 1, be accepted by a halting Turing machine M, where L is equal to the language of the Turing machine M. So time uh, of the Turing machine M comma S being a input string, is defined as the minimum length of the run of the halting Turing machine M on input S belonging to 0 comma 1 star. And let there be a function f which goes from natural numbers to natural numbers, such that for all S, so we can do this. We can give an upper bound on the time of M comma S. So, and f of s being the size of s. So if f is given the size of s, it spits you back a number, and time of m of s can be enveloped by this particular function f. Okay. Then we have found a function that is like an upper bound to the running time of the halting Turing machine m. Okay. So if m is deterministic, then we can say that L belongs to d time f. So d just representing the determinacy, which, if you remember, when I in the Turing machine example, I said that during in the delta function, in the transition function, if they were only one set that the particular state goes to, it doesn't have a many options to go to. So that would be non-deterministic when it has multiple options to, which means that the language L can be determined by a deterministic halting Turing machine whose runtime can be upper bounded by the function f. So P is best defined, say, mathematically in these terms. So you take an union over all, say, natural numbers, and you do a d time of n to the power k. So all problems that can be solved by Turing machines in this framework would belong to the complexity class P. Its language are its elements are the languages that can be solved by a polynomially running halting Turing machine. And NP is when you replace a D with the n time equivalent. Like I said, you have for the Turing machine from where the transition functions for each of the step can have more than one possibility. So that is the NP complexity class. Okay. So P time. The class P contains decision problems with an yes or no answer that are solvable in polynomial time with respect to its input size by a deterministic Turing machine, whatever I mentioned earlier. examples. So that should be that should be better. And here I want to also give you a flavor of the kind of research that complexity theorists do. Okay. So given two matrices n cross n, A and B, the question can be, is B a square of A? Say a question of this form. So the trivial algorithm that we can think of can solve this problem in O of n square. But we know that there's this person Strassen who came in 1967. He came up with a better way to sort of shave one particular addition and multiplication. Okay, so he showed that matrix multiplication can be done in a clever way in n of log of 2 of 7 many steps. Basically, he could break it down into such a nice trick. So that turns out to be n to the power 2.80735 and all that. So say people who are in the complexity theory community, they look at this problem called matrix squaring, and then they go on. So not this is not the complexity theory community. So this is like the algorithms community. So what they will do is they will try to shave off this 2 to the power 2.8 factor. Okay, and how low can they go is like the kind of questions they would be asking.
And
And
that's a respectable PhD.
that's a respectable PhD,
Yeah.
exactly. And and say people like say it has, so now you can see, right? Like so the lowest that you can go to is n square, because you have to at least read the matrix. But but what is like that optimal alpha that you can get to, right? 2 point what alpha is there? So there are these people called Josh Armon and Virginia Vasilevsky-Williams who have something of the form 2.37 to whatever that number is. How they come up with, please do not ask me. That is like a pure talk of its own, right? And I'm pretty sure like someone who is working in matrix multiplication would only in his head he or she would have only matrix multiplication hacks going around. How do we shave off time and steps further and all that? And the interesting part over here is, I think, for the complexity theory community, so whatever these algorithm designers come up with as techniques, so they will base their techniques on some, say, mathematical formulation. Okay, like some. So I know a bit of this. So they will encode this problem into a tensor product problem, and they will be trying to shave off certain operations of the tensor product and all, similar to how Strassen was doing. And the complexity theory community will try to say ki, like, with this particular method, this is the best you can get, these are the lower bounds you can get, which is again mind blowing if you really realize. So they are giving you in the abstract domain of all these things some numbers with which you cannot beat this. So therefore, like, now the research on the algorithm side would be, what can be another technique which is different from the ones that we were applying before, which can take the time complexity even lower. That is the kind of flavor of research that goes on in this area. Another example, primality. Given an integer n and its binary representation, in its binary representation, can we figure out whether n is a prime number? So this is something that India is proud. I mean, like, Indian academia is proud about. So AKS is Agarwal, KL, Saxena. So before AKS, if D is the size of the binary representation of n, then testing primality could be done in d to the power O of log of d. Okay. So this in practice would never exceed 8. So you can think of it as d to the power 8. Okay. Uh, but probabilistic, but there were faster methods where you trade off determinism for the existence of, you allow the existence of false positives to happen with a low probability, and it can run in O of t into d cube with the error probability of O of 2 to the power minus t, where t is the number of times we run the algorithm. So you sort of boost, uh, you run the algorithm over and over again to have a more confidence key. This number is actually a prime or not. So this is the nature of any probabilistic algorithm. But then this trio of Agarwal, Kyle, and Saxena in 2004, this team at ITK, and interestingly, Kyle and Saxena were students at that point. Agarwal was the professor. They proved that primes belongs to P. So they have a deterministic algorithm. It looks, the flavor of the algorithm comes from algebraic number theory, and it gets the running time down to d to the power 7.5. So you shave off things like this. Okay. So this is the nature of the problems in say the area of algorithms and complexity theory. Okay. So another complexity class, NP. So I've mashed together certain things. So definition NP, as given before, you take the non-deterministic n time non-deterministic polynomial with whose upper bounds for any of the running time is in polynomial of any number n. Uh, uh, and the solution verifier. So how do we say a language L is an NP if and only if there exist polynomials P and Q and a deterministic Turing machine M. Okay, so now you talk in the set in terms of a deterministic Turing machine M, such that for all string that belongs to this particular language L, you can find out a certificate. There exists a certificate in from the space of all strings, such that the size of the certificate is a polynomial of the in is a polynomial is in length polynomial to the input size, that input string size, and time m comma s hash y, which is like a concatenation of the problem and the certificate, is within another polynomial q, which takes a combination of these of this time. So therefore, this deterministic Turing machine is able to verify the certificate in a polynomial time. So this is how it is best to sort of think of NP problems. So some examples of NP problems, just two examples I've given. So PL is a propositional logic formula. I'll actually give an example of, I'll go a little bit deeper into PL. So if you have a formula in propositional logic, there exists an assignment V to the variable such that V satisfies. So this the way of writing this is V satisfies this particular formula phi of propositional logic. So the set of all such uh, this problem setting is a problem, a computational problem in the domain of NP, because once you are given an assignment which is actually polynomial in the size of the variables, in fact actually linear to the size of the variables, you can actually plug in the values to the variables and check and decide whether whether the variables whether the assignment makes sense or not, whether it is correct or not. So that is an NP kind of a problem. Similarly, three colorable problem where you are given a graph with a set of vertices and edges. You can apply three distinct colors to all its vertices, such that for all u and v, if u comma v holds, then u and v have. If there is an edge between u and v, then you have that u and v have different colors. So again, something similar. You will be given a color assignment to the graph, and you can verify whether this is true, and say you will do a check in n cube many things, like take any three of them and see whether they always satisfy the conditions, any two of them, in square many ways of checking this. So again, very quick, very rushed, but I think complexity theory have given a flavor of what kind of things are going on over there. And this is the beast. Okay, so there are like just too many complexity classes, and they have their own stories and stuff like that. So for instance, RP, randomized polynomial time, they talk about the resource randomness. NL is like log space. uh, I've forgotten what BPV is, but I think this is like bounded polynomial time in randomized setting. Then there are IP, which is like the interactive theorem proving space. I think yeah, EXP time is exponential time, and EXP space is exponential space. ZPP, I think, is where you can do RP intersection co-RP. So randomness, where you can have bounds on both sides, with bounds on whether false positives and false negatives happen. So that, I think, is ZPP. So anyways, I don't want to get into them, but I just want to give you the sense that it's a huge area, and people are daily discovering new things and coming up with new ways on problems in this. Phew. So I think I'm in time. We got to the midway point. So mathematical logic. What is mathematical logic? It's very hard to define what mathematical logic is. Uh, I think, in words, if I can, a logic consists of a formal or informal language together with a deductive system and model theoretic semantics. So I think most of it wouldn't make sense, but at least uh, I can express logic in these terms as best as I can. I'll none of these will be required, but I think the best way to do this is by giving you some sample logics. I'll try to introduce propositional logic, first order logic, second order logic in a bit more detail. And then I will mention about first order logic with these fixed points because the theorems will be based on them. But I'll not get into details of it because that is again another talk in itself. Okay. So propositional logic. So propositional logic, I'll give you the most details on. So how do you sort of describe a logic? You sort of give a syntax to it. So in general, you can think of logic as programming languages over. So logic sort of delineates syntax and semantics. So this is like the first. So what we sort of assume very implicitly now, right? Like when we are programmers and coders, you write a program which is a syntactical representation of a problem that you're solving in the real world, right? The real world is your semantic world, and programs are just very syntactic variables that sort of are able to do certain things on which you give meaning to, and they are able to do certain things. And logic was the first framework where you sort of even question key whether all semantics can be captured by syntax or something of that sort. Okay. So everything that we take for granted now comes out of the questions humans were raising in that time frame. Okay. So I think this starts off with Hilbert, then Gödel comes in, and then Turing comes in, and all that. Okay. So proposition logic, what is that? So you have a set of propositions. You can think of them as variables in a certain sense. They are not variables. They are true and false. They can only take true and false values. You have these logical connections of negation and uh, or. Okay. And then you define the set of all possible languages inductively. You have a set of formulas PL. You say ki like phi belongs to PL if and only if the base case would be you can write a proposition P belongs to this set of countable set of propositions, or you can negate phi, or I mean if phi belongs to that, then you can negate phi and you can take another phi prime and you can do an or with that. Okay. So the way I've written it is incorrect. You should be saying ki like if phi prime belongs to PL, then the set of all PL formulas is say of you can make them inductively on this one. Okay. So semantics. So now you have, but these are just symbols. Okay. They have nothing to do with true and false yet. Okay. They are just formulas they are just strings that you can write on a pen on a string on a page, that kind of a thing. So semantics are where you give meaning to the strings that you have. So a valuation function, it takes the countable set of propositions and assigns them true and false values. So each P0, P1 will take either a true or a false value. Inductively defined valuations for all formulas. So you can understand if you define P, then any of the formula will contain, say, these propositions. And if you know the values of each of the propositions in the base case, you can compute the value of the formula in the uppercase. So you have to give definitions for what do you mean by negation of phi and what do you mean by phi or phi prime. So you have to write them in a meta language to say key you can inductively define these definitions. So I am short of space and time, so therefore like those are my resources. So I'm assuming somehow with words I'm able to pin that picture in your head. So V being a valuation satisfies phi if and only if, say, this inductively whatever the valuation function you can get on phi results in true. Okay. An example of a proposition, which is a little sad on my end. The price of Intel stocks will rise by 5%. Say this is like a statement. Currently, with, with whatever is going on in the realm of Intel, I'm not sure whether I can give a true and false value to it. But yeah, such statements would would form in the realm of what you think of as a proposition. So with this brief introduction to proposition logic, which you understand, like the SAT solving community and I mean, proposition logic in its own domain is beautiful and people study it thoroughly. Like the entire point of having the SAT solvers, right? Like is trying to see whether, even though theoretically we know like these are hard NP problems, but can we still crack at it, right? Like humans are known to be adamant, and like you also understand that there are problems which will take a hell lot of time. You cannot possibly do it with your machines. I mean, like, because you have theory is like a, how do I say, theory is like a nice enough blueprint to go with on reality. But it also turns out ki, like, for the practical instances that you sort of have sat encodings for, they are solvable by sat solvers running for a week or month, so stuff like that, right? A lot of mathematical problems, puzzles go through the sat solving framework. So okay, first order logic. First order logic is a logical system for reasoning about properties of objects. You augment the logical connectives from propositional logic with predicates that describe properties of objects. Uh, should have given examples actually. Like for instance, the edge relation in a graph, that is like a, so your graph, the set of vertices are your domain, and the edge relation of the graph, when you say that two particular points in the graph are up, there is an edge between them, that is like a predicate. You talk about a property of that particular graph that you have. Functions that map objects from one to another. So you allow for say like the coloring, right? Like for each of the vertex you can give a color to that. So those would be the kind of functions that you can have. And quantifiers are like, there are two quantifiers that we will be using, the existential and the for all quantifier. They allow us to reason about multiple objects simultaneously. So a particular string that we write, say for all x fx, it would try to say ki, like, over the domain, all possible objects that you have, they will all satisfy fx or something like that. Okay. So this is like the, so we add in more expressive power to our vocabulary and our language, and that is the FO logic. So you can think of these as like programming languages. Like you had a very primitive programming language in the propositional logic sense, and then you give more power to like write more succinct ways of writing. So you can write down whatever you want to write in FO. At least over finite models, you can write down properties of FO. I mean, the things that you want to write down in FO as a propositional logic. Okay, like when I'm saying for all x fx in a finite domain, you can do an and over all elements of the domain and do fx. Okay, that would be like a large formula. But like when you write down as for all x fx, it's like a more succinct representation of that particular thing. So you can think of this as like, from assembly or transition to Python, you're a lot of things are abstracted away, and you are you are having more succinct programs that, of course, if you unroll, have large assembly codes and C codes underneath, kind of thing. So to get comfortable with FO, so I'll just first have this like picture. This is like a string. It might not mean a lot of things to people who haven't seen it. So I have n comma plus that I have in red. Okay. And I'm saying it satisfies for all x, for all y, for all z, x bracket open x plus y. This plus is again black. Okay, it's not red. And plus z, which is equal to x plus bracket open y plus z. Okay. So on the right side, this particular thing, this is a string. This has nothing to do with anything. This is a legal FO string. No meaning that you can assign as yet. On the right hand side, this is the semantics over which you want the string to be evaluated over. So n plus is called a structure, where n is the domain of the structure, and in particular by n I'm meaning the natural numbers. And apart from these, you have an interpretation function iota that has the following feature, that this particular uh, I mean, this symbol of plus that we see over here and the string that we see, that gets mapped to the function or the relation plus in the structure that we have. Okay. So this plus is what we sort of in general assume key a plus b is equal to c if and only if, say, so it will have tuples of the particular form 2 comma 3 comma 5, or like if it's a function, then you will have like 2 comma 3 gets maps to 5 of this one. Okay. So you have a structure, you have an interpretation, and you also have a valuation v over for all the variables. So for each of these x, y, z, this valuation function will map them into a value in the domain of natural numbers. Okay. So once you have all these things together, so n comma plus and the interpretation function and the valuation, they make up what we call as the model of natural numbers. Okay. So when we talk about model, so in general, I mean, someone who is more conversant with in the community, when they just mean this to be the model, but this is actually the structure. And the model also has these hidden interpretation functions for each, say, symbols that you have, and a valuation function for each of these variables that you have. Okay. So I haven't given you how do you construct formula. So that is like a missing piece to the puzzle. I am hoping I'm at least inspiring you guys to like sort of go and look into those kind of things. Okay. So yeah, and this particular formula, when you give the syntactic meaning to it, like over the set of natural numbers and addition, it captures the property of associativity for the addition relation. Okay. So you're saying basically x plus y, you do x plus y before you add it with z, and or you do x and then you add it with whatever the value of y plus z was. So this is the property of associativity. Since the model of natural numbers has the property of associativity, we say that the model satisfies the property of associativity. So this is how we state things in FO. Example of something that is not satisfied. Okay, so this is interesting. So you have natural numbers multiplication, you have a less than operator, and you have zero. Okay, zero as a constant here, zero as the representation of the constant symbol here. Okay. So here I have not colored it, but you have to understand this zero and this zero are different. This is the string zero, and it gets mapped to the value zero that of natural numbers that we have. So if you say there exists x such that x square is less than zero, in the set of natural numbers, this cannot be solved. This is not satisfiable. Okay, because there is no natural number for which its square can be a negative number. It's always positive. But in the domain of complex numbers, so you shift from the domain of natural numbers to complex numbers, you can have a particular such element of a complex number. That's how it's the uh, imaginary number. Okay. So these are the kind of things. So basically, you use FO to reason about mathematics in general. So you talk about, so in your head, in there would be this. So mathematicians, they sort of use logic is the language, is the formal language with which they talk about some semantic properties of a Platonic realm that they're talking. So the natural numbers plus addition, this is like in the Platonic realm, there exists this natural numbers, there exists this addition function, and you sort to talk about them with our colleagues, we have to write it down and then show and discuss. You have a vector space, which is something abstracted away, n-dimensional and all that. You have a representation of it using pen and paper. You say like these particular symbols, they actually mean something as an n-dimensional vector space and all that. And then you can do algebraic operations. Then you can do term rewriting kind of operations on the symbols that you have. So that is like the deductive system of logic that we are talking about. So you can play around with them once you have assigned proper meaning to what these symbols are. And that is what we do in programming as well, right? Like say Uber, in a certain sense, they abstract away a driver to a particular data type inside a program, right? So a driver is a human, physical living human with his or her own biases and so many intangible properties, semantic properties that we perhaps cannot account for. But for the purposes of Uber and Uber's functioning, we can have very important aspects of, say, the driver, whether he or she is nearby, whether they are accepting the ride or not, the value that the driver will see from the customer, or the path that the customer will feed and all. So this is the kind of flavor. This is now we take for granted, but these kind of things started off during I mean, when mathematicians were trying to formalize what they were doing. Okay. Second order logic. Again, I'll very briefly just touch upon things. So this augments the logical connective from FO with quantification over predicates. So you sort of not only are able to sort of access elements of their domain or relation between elements, you are able to quantify such possible, I mean, uh, predicates also. Okay, you can say like there exists a edge relation of this particular graph satisfying these other properties of this sort. Okay. So now second order variables. So in a certain sense, you can go over sets of the domain elements in first order logic, you could only access particular domain elements. Now you can take sets of domain elements in the second order setting. Okay, subsets of the domain. So, and I just give you an example of what existential second order is. It is an existential fragment of second order logic, which takes the form, at the starting of it, you have their bunch of there exists operator with second order variables tied to it, and phi being a first order formula. Okay. An example of this is like, I'm mentioning query, which I'll come to later. This two colorability of a graph or not. So you can write this down. You can so if in your head the model is clear, you're talking about in the space of all graphs, then what do you write down on pen paper to sort of say ki, like this graph will satisfy this particular property, right? So you write down ki there exists R such that for all x for all y, any edge between two elements of the graph will either be satisfied by the relation or not satisfied by the relation. Okay, that will capture two colorability. For three colorability, you need to come up with three such relations, R1, R2, R3, and you say ki like you have to say ki like each of the vertex shall satisfy one of these relations. It can be red, blue, or green, and then if there is an edge, then it can either be a red or be a blue or be a green. You have to encode it out. It's a bit of a task, but whatever you think of programmatically, you have to write down that thing within the framework of first order logic, these languages that we have. So think of this just as programming. Like, say FO gives you syntax and semantics of how to write down things. So you have to write. So if you want to write down two colorability, how would you code, say, that in the FO language as per se? Okay. So FOLFP, okay, this is, I'll just touch upon it because a lot of theorems will be mentioning this. So you augment the first order logic with the least fixed point operator called the LFP operator, which operates on the subsets of, so in a certain sense, it operates on the subsets of the domains of the power set of the domain, subsets of the domain or the power set of the domain, and is able to extract particular subsets which will be definable by the LFP procedure. So what I want to say here is like LFP is in between, say, FO and second order logic. You are able to get second order quantification, but only limited. You are not able to get all second order quantification. You are able to only get second order quantification that can be accessed through this least fixed point procedure. Okay. And I'll just give a brief hint of what that is. So firstly, least fixed point quantifier induces an operator on the power set of elements on the structure ordered by inclusion. These are just words. I could have written them down in mathematics. I was thinking whether which is terse and which is more verbose. I had to do a trade-off. There is a positive restriction, etc. You don't have to know what that is, but there is a for finite structures. We know the LFE procedure will halt in a least fixed point. There is because of the theorem by Naster and Tarski. Okay. And what does the procedure look like? So whatever the LFP operator is, it operates on a sequence of sets beginning from the null set, empty set, and then it iterates over and over again from the function that computes the particular previous set of it. Like you start off with f of the null set, and then you take the next set, which is which operates on the set that results out of the operation on the null set, till it reaches a fixed point where fn of the null set is equal to fn plus 1 of the null set. Okay. So I have not given an example of it, but this is a particular logic FO. So you're extending FO with different quantifiers. In the second order setting, you give too much power to it, and in the LFP setting, you restrict the power in a clever way. And these are the kind of things that say logicians who are looking into complexity theory, they were trying to see what can I do, what are the trade-offs I can do with the expressivity of the logic to capture the complexity class. And this is where we'll get to logic L captures the complexity class C. So first I'll just talk about what a query is. Query, let F be a class of finite sigma structures, and let K be a number from the natural numbers. A k-ary query on F is a mapping Q defined on the class of finite structures, such that if A is a structure in F, then QA is a query relation on the domain of A. Okay. So if we hadn't written as for all x, for all y, for all z, then these variables x, y, and z, these would have been free. Okay. So which means ki I would have a formula where I have three variables x, y, and z, which are of the form ki x plus y plus z is equal to x plus y plus z. Okay. And this will give you a three-ary relation on the set of domain of natural numbers. Okay, that is what I mean by a query. So these has relation with say how databases and all. I mean, I'm not sure which came first, which came later, but the ideas of them are very similar. Okay. And I have expressed key, like say there is a formula phi belonging to a logic L, where phi is a formula with k free variables, then it defines a k-ary query on the set of finite structures that you talk about. Okay. So a logical characterization of the complexity classes. So to get to the setting, we need to have a complexity class, we need to have a logic, and we need to have a class of finite structures. So this is where the semantics of it. So in general, for the theory community, we talk about the set of finite graphs. That is, so graphs are very interesting. Graphs are general enough to talk about any other superior structures. You can encode any other superior structure from whatever we have as graphs. Okay. You can encode those structures as graphs. Okay. So that is why graphs are very interesting. Anyways, give you to concretize whatever the statement above is. So let C be the polynomial time P, let L be say FOLFP, and let F be a set of binary encodings of natural numbers. So a particular logic, a particular language in this particular class of finite structures would be say the prime numbers L. So the binary encodings which are prime, they will be a subset of L, F. And if so, this is not this I'm not saying, but like I'm saying hypothetically, if P could be captured by FOLFP, then what I would want to mean is that this language of primes can be written as a formula in FOLFP. Okay. So in a certain sense, whatever algorithm that you come up with, you can also have a formula in this particular logic to talk about it. And why do you want to talk about things in a formula setting? Because logic has a lot of tools to talk about the limitations of expressivity of a particular logic. Okay. So this is so the ideas that came about in this particular thing, if you were trying to solve this question of P not equals to NP, then complexity theorists were always getting into a bottleneck of what kind of tools do we use. So logicians said ki, like we have a lot of tools in the talking about expressivity of logic, of each of these logics that I talked about, like FO, proportional logic, like the FOLFP and all that. We want to sort of see whether the tools we can use to talk about distinction, to talk about like what can be done and not done in this thing. So that would be like a language that is expressible in FOLFP, but not expressible in another logic, which is capturing another complexity class, and that is how you want to sort of separate out the two complexity classes P and NP. Okay. So this is the holy grail of the research, but we haven't gone there yet, of course. Otherwise, this would be news basically. So we say that the logic L captures C on F. This is how we state it. If the following hold, the complexity of L on F is C, by which I mean that for all formula that belongs to this particular logic L, and for all structures that belong to this finite class of structures, you are able to say that this particular language phi such that phi satisfies this is called the structure A, the math frac A. I mean, so A such that A satisfies this particular formula phi. This particular language that you have, that is within the complexity class C. Okay, so this is in one direction. So in a certain sense, you can say the union of all formulas. Uh, so if this was written as a language of phi, L of phi, okay, when you know these things are constrained, so you say ki the union of all formulas of L, so for which L of phi exists, that will be a subset of the complexity class C. Okay. And this is like one direction, and on the other direction you would want to say key like for every property p on the structure of f. So I will talk a little bit about the property p that can be tested within complexity c. There is a sentence phi p within L such that this particular structure, if it satisfies phi p, then phi has the property p. Okay, for every a that belongs to the structure S. So what do I mean? So this is, I think, very convoluted, and this is of course has to be convoluted. This is like I mean, these are very complex ideas that get into the picture. So what is a property? A property, so a property is, wait a second. Property is say P is a property on F if for all A and B that belongs to this class of finite structures, we have, if A is congruent to B, isomorphic to B, then A has the property P if and only if B has the property. Okay. So this is what we define as what a property is. What does it mean for a property P, for a property P to be true in structures from F to be tested within complexity class C? It means that for some subset F prime of the set of finite, of the class of finite set uh, objects, the problem of checking whether for all x belongs to F, does x belongs to F. So this is like the membership problem of F prime, this particular subclass of F, x being each element of the class, can be decided within the use of the complexity resources given within the complexity class C. Okay. Then you say that the property P of structures from F can be tested within this complexity class C. What does it mean for every property P is satisfiable of for all structures of F can be tested within the complexity C? It means that we are interested in for all such possible subsets of F for which the membership problem of this F prime can always be decided within this complexity class C. Okay. So this is a lot to unpack. I'm not sure what is the best way to do this. Perhaps someone who is more experienced would be able to put it in much more simpler terms. I could unfortunately unpack it in this way. Okay, so this is my lack of, how do I say, of understanding it at that detail that I can speak it in terms that can be accessible to people. Okay. What does it mean for every property P? There is a sentence phi P that belongs to L. It means that for the property that we are interested in can be expressed using a logical resource of the logic L. Okay. That is, they can be expressed as a sentence phi P that belongs to L. So this is how you sort of combine complexity and the logic. So the complexity is talking about some other resource. It will perhaps be time, it will perhaps be space and all. And you connect it with logic. Okay, logic is this expressivity resource. Okay. Okay. Okay, I think we have taken a lot of time to finally get to the meat of the things. So what are the kind of theorems that are there in this area, and why should you be even looking into these things? So let's start off with Fagin's theorem. I should have given the dates. I'm sorry for that. Yeah, but I think it's in the order of things that has happened. Fagin's theorem, let Q be a query on the class F of all finite structures. So this is like a very powerful statement. So in general, you understand that this is so generic that getting even one particular theorem is very, very hard. Okay. And this is the birth of it. Like Fagin gave most general kind of statement that you can think of. Then the following statements are equivalent. This particular query is an NP, non-deterministic polynomial type, and this query is second order existential second order definable on F. Okay. In other words, there exists SO captures NP. Okay. So that means ki any non-deterministic polynomial Turing machine or any non-deterministic polynomial algorithm that you can think of, you can also equivalently write down existential second order formula for it. Okay, that's like a huge power. Okay, and for second order logic, there are very good tools to sort of delineate where the second order logic, what are the limitations of second order logic, what it cannot express and all that. Okay, so there are techniques, Aaron for phrase EF games. I don't know how to best pronounce them. but like the shortest way I call them is EF games and all that. So there are EF games 0-1 laws to sort of delineate expressivity of aspects to logics. Okay, what can the logics not express and do? Okay. So we started off with Fagin's theorem. Then this is the famed Immerman-Verdi theorem, where we very close to P, and it's like a taunting theorem. Okay, it's like someone who's in the community would feel like you are so close to asserting polynomial time. So you polynomial time is actually very complex. Like if you really think about it, what does it mean to be talking about polynomial and all that? Like, but this gives you a more structured way to think on things. So if
Is
Q is a
this
query,
Moshi, by the way? Is it Moshi Vardy?
yeah, this is Pushavarti. Yes,
Okay.
yes,
So
yeah.
he's dominating not just formal methods, but also
He's
complexity
yeah.
theory.
It is his
Nobody
PhD
can beat
thesis, I
him.
believe. It is his
Okay.
PhD thesis. Okay, so I even reached out to Moshe saying, like, what do you think can be done further in this area? He said he was not optimistic about it. So I'll also give you that. So this is like a trap that you might get into. So yeah, that part I'll talk about in the end. Yeah. So let Q be a query on the class of F of all finite ordered structures. Then the statements are equivalent. Q is in P. So okay, you don't talk about all finite structures. You give this notion of ordered. Okay. So I can talk about these in detail, but let me just describe the theorems. So Q is in P and Q is LFP definable on F. Okay. So in other words, P is equal to LFP on F, but this F is over finite ordered structure. So if this was not ordered, then polynomial time and LFP are equal. Okay. So this is like a subclass of polynomial time in a certain sense. Okay. So the other theorems, so the another theorem that extends LFP logic with a counting quantifier. So logics are not very good at counting and all that. You cannot talk about evenness, mod 3, these kind of things. You can talk about, say, values that this can take and all that, like whether a particular set is at least greater than 5, at least has 5 elements, whether the set is non-empty and all. But you cannot say the domain is even or something of that sort. Those are hard to do in at least FO, I mean lower logics. So you introduce a counting operator. You give it power. Okay, fine. You can do some counting, and you restrict itself on special classes. So, like I said, the generic results that you saw to before, they're not going to happen every time. So you have to restrict it on finite structures of combinatorial or graph theoretic interest, and then you can yield some theorems of it. Okay, in these special structures, it is possible to define a linear order in LFP, which makes it yield a logic for P in such cases. Okay, so this statement that I made of order. So this order you can extract out from certain properties in these special combinatorial and theoretic objects. So what are they? So this is Martin Grove. So polynomial time. So on the class of all planar graphs. Okay. So planar graphs are graphs where you can actually uh, draw the graph on a sheet of paper without any of the edges crossing each other. Okay. So on the class of planar graphs, P is equal to LFP plus the counting operator given to it. So it's a very powerful thing. So you're very close to polynomial time, but over the class of planar graphs, you are not talking about all graphs in general. Okay. And so this is graphs of tree width. I don't want to go into what tree width is, but similarly for P is equal to LFP plus C on the class of all graphs of tree width at most k. Okay. Another theorem that I would want to give, there is also a different fixed point operator. So now you can also change the fixed point operator, right? And you can play around with, say, partial fixed point. This leads to some another logic called PFP logic. So this is more powerful actually in a certain sense. So if I give the definition, you will understand why it is powerful. Uh, Let Q be a query on the class F of all finite ordered structures once again. Then the following statements are equivalent. Q is in P space and Q is PFP definable on F. So in a certain sense, PFP is equal to P space is equal to PFP on this class of finite ordered structures. And PFP logic is interesting because it simulates an extension of FO with a while loop procedure for recursion. So this is the programming language theory mixing with the very abstract out things out with logic. So I think with this, I come to an end, and within time, I wasn't sure I would make it. Yeah. And yeah, complexities who I think Max has given nice things. Yeah,
For me, that
so
was
yeah.
that was a wonderful presentation. Thank you so much.
Okay, thank you so much.
And a
Yeah,
marathon. I'm impressed that
it
you
was a
covered all
marathon.
that
I had to
material.
I had to complete. And you understand, descriptive complexity has to be a marathon, right? Like
Yeah.
it's three areas you sort of mash